Okay, so I wanted to make a quick video demonstrating taking a frequency measurement from my signal generator on my new 2465A scope, and then compare that calculation to measurement from my frequency counter. So first thing we want to do is look at the trace on the scope. Now, right now the 652A is set to approximately 1 kilohertz. I've got the multiplier set to times 1K and the scale set to 1, although if you've watched my previous videos you know that I discovered that the calibration on this oscillator is somewhat off, but it's just fine when used in conjunction with a frequency counter such as this HP unit or Lectrotech or any other frequency counter capable of those frequencies. Anyway, before I talk any further, let's go ahead with the test. Now, I've got a BNC coming straight from the oscillator right into the scope. I've got the attenuator set to safe levels, although this scope's capable of equal to or less than 400 volts peak on the input. I don't know if that's AC or DC, but I'm going to respect it either way at the moment. So here's the trace on the screen. Because we're not using a probe, I'm pretty sure that the volts per division isn't going to be calibrated, but right now we're just doing a frequency calculation, so it doesn't matter. This video, by the way, was inspired by Alan W2AEW, and so I just kind of wanted to do the same with my equipment. So, got the first zero crossing here, and then we can count 1, 2, 3, 4, 5 gradicules. Now I'm going to say 5 1/8, so grab my pencil, see where I laid it down. Oh, here we go. Got a pen. So here's the formula. So you count the number of gradicules, multiply by gradicules per division times seconds over division equals your period. So we've got, in this case, we've got 5 1/8 times, let's see, okay, seconds over division, so in this case it would be 200 microseconds. Let's convert, and you want to keep your units straight, so 200 microseconds would be 0.002, because if you filled it out then you'd have 6 significant digits, so you'd have microseconds, but that's irrelevant for our concern here. So, and as we know, we can cancel out here and multiply 5 1/4 times 200 microseconds, which gives us 1025. 1 divided by 1025 gives us this result, approximately about 976 or so. So that's our frequency, a little bit under 1K, according to calculation and according to the scope, the measurement the scope made, assuming that I even got this correct. This may be less than 1/8 here, or a little bit greater. So let's go ahead and do as Alan did and verify with a frequency counter. I was borrowing the power cord from my HP to plug in the scope, so we're just going to use the Lectrotech at the moment for this. Let me put down the pen. Give the slow time base a second. Whoops. Plugged in the wrong end. Here we go. That's what I get for videoing and measuring at the same time. Okay, 966, 975. Seems to be pretty stable right now at 966. There we go, we dropped to 9. Okay, so it looks like we're about 100, 110 hertz off, something like that. So really, if I recall correctly, this is pretty close to what Alan got, so I don't feel so bad about some of this equipment. It'd be nice if I had this counter plugged in right now, but I didn't think of that. I've got plenty of power cords in the drawer, so I'm sure you'll see that in an upcoming video. So take this out, plug it back into the scope. Now if I move this, of course, you know, kind of have some fun watching the frequency change like that. Of course we can change it in large increments. As we go down in frequency, we're almost flat here. Repeat that, I may have had it off the screen. See, now you're almost just looking here. You're only looking at the RF envelope of the carrier, and you actually have to slow down this time base in order to see the sine wave again. So now we're back at 200 where we started. 1 megahertz. Smooths out even more. Turn the intensity up a bit. Okay, KF4 DBK.